Population growth refers to the increase in the number of people living in a specific area or across the world over time. Population statistics also can be influenced by several factors such as vital statistics and migratory movement. The vital statistics consider the number of live births and deaths as well as their effect on natural population increase. The migratory movements discuss population inflows and outflows as well as the resulting migration patterns. But in this context, we are discussing population growth, which occurs when the number of birds and people moving into an area is greater than the number of deaths and people moving out. Thus, in this task, our primary concern is the application of the first-order differential equation on the growth of population in Mexico from 2000 to 2020. We are going to apply the Malthusian growth model to find the population growth in Mexico. The Malthusian model can be written as above. Therefore, for the MAT097 project assignment, we are going to achieve the objective of task 1, which are to use the Malthusian model to estimate the population growth in Mexico from 2000 to 2020, to compare the graph of actual data and calculate the data, to predict the past and future population in Mexico using Malthusian model, and to identify reason of the expected value of past and future in a particular solution.
Next, we move to the table of data. The table shows the population growth in Mexico from 2000 until 2020. We obtain the data from the World Bank Group data website. Moving on to the graph of data, the graph shows two lines, blue line and red line. The blue line indicates the actual data that we obtained from the website, while for the red line indicate the solutions that we obtained from the particular solution calculations.
Now we move to step 2, task 1. So let the P function of T become the number of population in Mexico present at times. So since the rate of growth populations is directly proportional to the number of populations, so we got dp over dt directly proportional to the P. So we got the dp over dt equals to kp. So now we'll rearrange the equations. And then we integrate the equations, and now we rearrange this again. And we will change the P. Right now we got P equals to plus minus exponential power of Kp multiplied by E exponential power of C. So right now we change A. We let the A equals to plus minus exponential power of C. So right now we use the initial condition T equal to 0 at 2000, which has this population. So now we change A to the number of population at years 2000. So now we rearrange it again. We change it to the long, and we will get the value of case. So right now we got the particular solutions. So right now we move to step 4, which is to find a value of future records. So right now we set the t equals to 23 at year 2023. So we got pt, and we use the particular solutions, which is this, and now we got the number of the theoretical values. So right now we will compare it to the actual value of the population in Mexico in 2023. So right now we move to step 5, which is to predict a past values. So right now we use t equals to -3, which at years 1997. So right now we will change the a equals to the number of the population, and we change the t in the particular solutions to be -3, and now we got the number of the past values. And also we can see the actual values is a little bit different from the theoretical values.
Hi everyone, now let's discuss on why the Malthusian model doesn't really work well when we try to use it for Mexico's population. At first, the model indeed looked okay. In 1997, the percentage error was only 0.34%, which shows that there was only a small difference between the predicted and real number of people. But as for the future estimation, which is 2023, the percentage error was calculated to be 6.84%. This is wrong because based on the calculation using the Malthusian model, there would be almost 139 million people, but actually there were only about 129 million. So why does the model get it wrong? As for the first factor, healthcare in Mexico got better. Babies are healthier now and people live longer. From 2015 to 2022, fewer babies died and life expectancy went up. This means people aren't dying as young anymore, which changes how the population grows, and this is something that the Malthusian model didn't expect. Next, families are having fewer kids. The average number of children per woman is now about 2, which is just enough to replace the parents. But in some rural places like Chiapas and Guerrero, families still have more kids. This difference between cities and villages makes it hard to guess population using just one number for the whole country. Also, Mexico has a lot of young people. About 1/4 of the population is between 10 to 24 years old. So even if families are smaller, the country still grows because many people are still in their childbearing years. To put it more easily, even if each family has fewer kids, there are still so many young people having kids. So the total number of babies being born stays high. This is called demographic momentum, and again, the Malthusian model doesn't really include this idea. Moving on to another factor, migration. Migration has slowed down a lot. Before, many people left Mexico to go to the US, but now that number is way smaller. This means more people are staying in the country now than before. As a result, the population doesn't decrease from people leaving like it used to. Sadly, the Malthusian model doesn't take this change into account again. And last but not least, Mexico's economy got better. Less poverty and more job chances for people. This means that people don't really need big families to survive, and fewer people want to leave the country. A better economy also means more people can afford healthcare, education, and stable lives, which subconsciously affects how fast or slow the population grows.
To sum up, this project gave us a real opportunity to put up what we have learned about differential equations into a practice. By using a Malthusian growth model, we were able to estimate how Mexico's populations changed from 2000 to 2020. We compared our result to actual data and looked at how accurate our prediction were, and even tested the model by predicting both past and future population numbers. While our calculation came close to the real values, we also saw where the model didn't quite match reality, which made sense, since real-world factors like migration, policy changes, and healthcare improvement can be captured by a simple equation. Still, the model gave us a solid foundation to understand population trends and how mathematical tools can explain them. Overall, these tasks help us to connect math with the real world. It showed us not just how to work with the first order differential equation, but why does it matter and how powerful it can be to turn numbers into insight.
First of all, as we all know, the area of trapezoid is 1/2 times y0 plus y1 times h. Next, we divide this interval AB into n subinterval with equal with h, where h is b minus a over n. Then, the area of the region would be the sum up of all area that has been divided, which is A1 plus A2 plus A3 and so on. Then, we will sub the area formula of trapezoid into A. And lastly, after factorize the h over 2, we will get the formula as stated below. Only the first vertical y0 and last vertical yn appear once. The rest vertical sides appear twice.
We move on to the question. So the question asks us to find area by using full subinterval. First thing first, set up the first row by x, fx, coefficient, and then coefficient times by fx in Excel. On the other side, we will put a, b, and n. So a is -2, b is -10, and n is 4. Then we want to find the delta x by using formula b minus a over n. So -10 minus -2 divide by 4, and you will get -2 for delta x. Next, for the second row, we will put a value which is -2, and then we will keep on adding the previous value by delta x, which is -2 until we get the value of b, which is -10. And then we will sub the x value into the equation to get the value of fx. Then we will obtain all these values. Moreover, for coefficient, only the first and last value will be 1, and the rest will be 2. Then we will multiply the x value with the coefficient, and we will get the all answer in 7 significant figures. After that, we will plus all the answer and get 85.50123. Lastly, we will do 0.5 times the 85.50123 and divide with delta x -2. And the final answer would be -85.5012. However, since area cannot be negative, we will ignore the negative symbol. And the final answer will be -85.50123.
Moving on to the age subinterval, basically it's just the same as the method of 4 subinterval. Therefore, the final answers will be negative 83.4999, but the negative sign will be ignored as area cannot be in negative form.